asked our speaker today to come in and give you all a little bit different of a talk than what you usually get. So his talk is very much more on the policy side of energy and then specifically nuclear technology. So because he wants to save the world like the rest of you do from climate change, right? We all are here because we want to do something positive towards the world. So his main motivation is motivated by the climate crisis. So he moved to DC, started up a research initiative, Energy Impact Center, that's focused on exploring nuclear power and its role in decarbonization. He has also the main thrust behind Titans of Nuclear, which is going around the nuclear field and interviewing very large names and young professionals as well in nuclear that will kind of provide a mapping for the future of anyone who's interested in nuclear power and kind of providing a humanized perspective to nuclear. So without further ado, I'll let Bret take it away.
Thank you. Thanks for having me here. You guys live in a beautiful city. I hope the weather's always this awesome. No? Okay. So I'm going to talk for about 30 minutes, and then we'll open up to questions for about 30 minutes. The first half is for you. The second half is for me. So let's get started with a pop quiz for the audience. What would be the result if globally we got to 0 new emissions in every single sector? Electricity, transportation, industry, heat, agriculture, 0 new emissions. Would the climate get better, worse, or stay the same? 0 new emissions, okay? So raise your hands if the temperatures would stay the same. Raise your hands if temperatures would go up. And raise your hand if temperatures would go down. Okay, a little bit of variety in the answers of the audience. Well, although commonly assumed, going net 0 does not leave us at the same temperature that we are at today. It leaves us at the same rate of adding heat that we are at today, a radiative forcing of about 3 watts per square meter. In mechanical terms, greenhouse gases act as a valve, not a sponge. I'm going to use an analogy here to make this point crystal clear. If you're driving towards a cliff at 30 miles per hour, that's the 3 watts per square meter, 0 new emissions is not stopping the car. 0 new emissions is continuing at 30 miles per hour. Another year worth of new emissions is driving at 30.4 miles per hour, then 30.8 miles per hour, and 31.2 miles per hour, and counting year over year. It is slightly worse, but as a society, when we're about to make decisions to the tune of tens of trillions of dollars, we should probably have that discussion. That either way, get to 0 or do nothing at all, you end up in the exact same place. And in this case, due to previous emissions and the sheer quantity of it, at almost the exact same time. Virtually all discussion in the media, the papers from policy wonks, everything you hear from environmental groups, politicians, clean energy startups, what you probably talk about with friends and colleagues, it is all to solve the wrong problem. Getting to 0 new emissions will have virtually no effect. So if this is the wrong problem, what is the right problem? Well, to avoid further warming, and this is to say nothing of the increase in heat that we've already experienced, we need to get the atmosphere back into a state of radiative balance. That's a bit less than 300 parts per million CO2. That means we need to remove roughly 1 trillion tons of CO2 from the atmosphere and counting. Now, if there's one thing that I can guarantee, removing that much carbon, removing 1 trillion tons of anything, and in this case, given how dilute the carbon is, much more than 1 trillion tons, that is going to take a lot of energy. So, since all of that energy is going to release more carbon, right, because everything has an inherent carbon footprint, how much is supercritical here? So here's the governing rule for any approach to solving climate change for which we must evaluate. Your entire capture system must permanently store more carbon than is emitted in its production and that of the energy source that it utilizes. When I left my life in Silicon Valley to start the Energy Impact Center, it was based on this premise: to discover the subset of solutions that could actually make a difference, that could actually go negative, that could actually stop climate change. You see, if you're not going negative, even if your favorite energy solution replaces a worse energy source, you're not actually making things better. You're still adding carbon to the air, which further increases the rate of heat addition. It's like punching a small hole in a sinking ship instead of punching a big hole and then claiming that you are helping the problem. Low carbon energy is not fixing the problem. Only extremely low carbon energy even has a chance. So, before I get to which solutions can go negative, and I promise that's coming, we're going to discuss one more problem that the climate change discussion has fundamentally wrong as well: the real role that energy plays for most of the world. Although we don't perceive energy very much directly throughout the day, it's far more than just gasoline and leaving the lights on longer. Energy is embedded in food, in medicine, in buildings. Energy moves goods and people around the globe. Energy is in everything that you need, and energy is a fundamental part of what you love about a prosperous world. Restricting energy, on the other hand, with higher costs, this means real hardship is spread throughout every part of life. The poorer you are, the worse it hurts. This is why we decide to subsidize all energy in society, even the dirty ones, because the benefits from inexpensive power have a truly profound impact positively on quality of life. For most of the world, especially the poorest, less access to energy could actually hurt them more than climate change will. And they would feel it immediately, every day, in everything that they do. Let's observe a very similar decision regarding energy access that humanity has already made. We knowingly continue to pollute the air with particulate, causing millions of cancers and asthmas every year just to receive slightly cheaper energy. We've had the medical reasons and technology to replace coal for over half a century. But the only thing that ever meaningfully has is another cheaper form of power. Do we really expect a worldwide consensus on sacrifice now, across all age, class, and creed, to combat a threat distant in time and place? What the climate elite ignore is that to anyone but the absolute wealthiest, electing for more expensive energy isn't consideration. Solution's coming, but one more thing before I get to it. We have to apply one more constraint. Whatever our solution is must not induce rapid changes to precipitation patterns. To many of the poorest on the planet, this would accelerate the worst possible outcome. We have over 2 billion people that do not have the agricultural know-how, infrastructure, or capital in place to adapt their food production to any sudden changes. And they would be forced to abandon their homes after just a few years of abnormal rainfall. So unfortunately, this pretty much rules out the cheap and quick geoengineering fix that some of you are probably thinking about. Even if it would have a long-term positive effect on crop growth, regional changes to expected water, too little or too much, can instantly send millions into starvation and relocation. Or worse, as we've seen in Syria and Central America, dire civil conflict. Let me drive this home. If we mess with precipitation patterns on a global scale, the second-order effects of food and water security could simultaneously destroy the lives of 1 million times more people than any wildfire, flood, or hurricane would. Okay, I promised a solution, right? Let's derive one from first principles. If your mathematical imperative is that we must account for previous emissions, and our societal bounding condition is that we must do so in a way that doesn't impose an economic burden, then we must take the very things that require energy and force them by definition to capture and sequester carbon dioxide. In other words, we need to make fuels and products with hydrocarbons, just as we do today, but with hydrogen and carbon from the air instead of from the ground. In this scenario, nothing downstream, not behavior or infrastructure, needs to change. And energy consumption all of a sudden has the exact opposite effect on climate. If you use carbon from the air, the more people consume, the more prosperity you enable, the faster we will solve climate change. If you want to actually solve this problem and do so in a matter of years, not decades, you just need to make carbon-negative fuels cheaper than carbon-positive fuels. This is a complete alignment of individual behavior, market forces, environmental health, and human well-being. But to do so requires extreme energy abundance and an extremely low carbon footprint. It's a high bar to meet. And when I started the Energy Impact Center 2 years ago, we ran this calculation for every known technology, and we found only one source that even came close to meeting these requirements. Not only is uranium an order of magnitude more abundant, but it has 6 orders of magnitude the energy density of fossil fuels. 3 million times as much energy. And to solve climate change, all nuclear power has to do is become just 3 times as cheap. In the last 2 years, my organization has interviewed over 1,500 experts across technology, industry, economics, policy, and more to figure out why this hasn't happened yet and what it would take to make this a reality. In that time, I've personally done over 100 site visits to research centers, power plants, universities, and conferences in over a dozen countries and asked over 10,000 questions along the way. This is all documented on the Titans of Nuclear podcast, which I welcome you to start listening to if you don't already. I will now give you a summary of what I've learned over the last 2 years and wrap up with a plan to get out of this mess. So, what's wrong with nuclear? There is one problem, and only one problem with nuclear, and that is building and operating new nuclear power plants costs too much. Before you raise your hand about public perception being a challenge, the facts simply don't support it. Orders dried up in 1978, before 3 Mile Island, because nuclear was too expensive. Orders dried up in 2008, before Fukushima, because nuclear was too expensive. Dozens of countries right now are desperate to build nuclear, but nuclear is too expensive. Public perception is a self-defeating excuse that nuclear engineers use for not building a cost-competitive product. We don't sell EPRs and AP1000s for the same reason we don't sell Segways. Over-engineering has priced it out of the market. If we come up with a cheap energy product, no matter what the critics say, the world will rationalize buying it the same way that we rationalize buying clean coal, natural gas, or toxic solar panels. The price of a modern nuclear plant is not driven by inherent complexity in what nuclear is, but rather a culmination of bad decisions that drive up cost, scare the public, and yet stubbornly maintain industry-wide support. My team has spent the last 2 years compiling dozens, but for now I'll give you 4. Number 1, large construction sites. I almost couldn't believe it when I saw Vogel bragging about 8,000 workers on site a month ago. Yes, more jobs are great, but what you want is 8,000 jobs across 8 different sites that only require 1,000 people each. Make a cheaper product, and you'll drive job growth by building more of it. Vogel's construction design choices have essentially guaranteed that there will never be another gigawatt-scale nuclear plant built on American soil again. That's bad engineering. Number 2, forged pressure vessels. Does anyone know why the industry requires forged pressure vessels? We didn't used to. Out of curiosity, I called up a few manufacturers to understand the difference between welding and forging. It was 100-fold. 1.5 million versus 150 million. The roots of this requirement come from experiencing radiation-induced embrittlement of the copper in the weld filler material back in the 1960s. But you know what? We've got new weld filler material now. And we've got processes that don't even require filler material at all. To stick with forgings is emblematic of how conservatism and tradition drives bad engineering. A good engineer does not design the strongest possible equipment. They design the cheapest possible equipment that meets strength requirements. Number 3, airtight containment. You guys know the difference between a hot pot and a pressure cooker? It wasn't a hot pot used at the Boston Marathon. Yet we require designing nuclear pressure cookers with hydrogen as the fuel and radionuclides as the shrapnel, increasing cost and decreasing safety. The design goal is to limit the flow of radionuclides in the case of an accident. That is antithetical to requiring a fixed volume in the presence of a heat source. No requirement for airtight containment means no pressure buildup and no hydrogen buildup. And 99% of the source term moves no more than a few feet. A few radioactive gases would escape, instantly dilute, and become totally harmless part of our atmosphere, just like the sun creates totally harmless radioactive carbon-14 in our atmosphere every single day. Instead of accepting a little radioactive gas escape, we create a dispersal mechanism for an otherwise non-mobile source and demand an incredibly expensive structure to facilitate this. Light water, or any reactors with inherently negative neutronics, do not need containment. They need confinement. A strong roof is both safer and 100 times cheaper. We sit here criticizing the Fukushima operators for keeping their generators in the basement when we sold them a plant that traps hydrogen. Let's take a little responsibility for our bad engineering. Mistake number 4, evacuation. As far as radioactive release goes, Fukushima was as bad as it could ever get for a light water reactor. The largest tsunami earthquake combo civilization has ever seen took out every single safety system, spilling 3 gigawatts of core melt on the floor. An expensive mess, but not a hazard if you just stay out of the room. But then our genius pressure cooker design shot it out of the building. And even then, it was in such low quantities that no one was ever at any risk. A competent emergency plan shouldn't even have evacuation on the table. But what's the nuclear way? We behave as if a meltdown is the greatest possible emergency that could ever occur. And we convince the rest of the world of that. So as a response to this attitude, the Japanese government went in, and the first thing they did is unplug 1,000 of their elderly from vital medical equipment, evacuating them from the remainder of their lives. After that, they forcibly removed 100,000 people from their homes for years while systematically destroying their land, all to clean up an insignificant amount of radioactive contamination. Chernobyl taught us exactly how much and what type of radiation causes harm. Fukushima proved that no light water reactor could ever come close in any circumstance. But instead of sticking up for ourselves and shouting from the hilltops that we should have less regulation than a campfire, we cower in fear and invent ever more systems, further driving up cost. Bad logic, bad leadership, bad engineering. Why is this? Why are some of the smartest people that I've ever met responsible for some of the worst design choices that I've ever seen? I've got 2 words for you. Safety culture. As students, I'm not sure if you've been brainwashed yet, but as a working adult in nuclear land, arguing for safety wins every argument, even if the result is less safety. Selling safety is selling fear. It scares the public. It doesn't appease them. Safety is responsible for those domes that built up explosive hydrogen. Safety is responsible for evacuations, which, unlike light water reactors, actually do kill people. And even worse, safety is responsible for driving cost in every aspect of nuclear power, pricing it out of the market, and enabling the proliferation of every other less safe energy source. If you hear your colleagues criticizing the Russians, consider this math. A Chernobyl every month for the next 100 centuries would be safer than letting coal persist for even 1 more year. And we are responsible for coal by not allowing society a cheaper option. When the industry says safety is our #1 priority, what they mean is selling safety is their #1 priority, not making the world a safer place. Let's summarize. In order to stop climate change, we need to remove 1,000 gigatons of CO2 in a way that doesn't require sacrifice. To do this, we need carbon-negative fuels and products that are cheaper than carbon-positive fuels and products. To do this, we need to make nuclear 10 times cheaper than it is today. How? $1 million question, right? Number 1, hire competent construction managers. Even with all the additional nuclear-specific constraints, it has such an overwhelming advantage from a fuel perspective, better project management alone can make it cost competitive. Build the plants to be smaller and be built faster, borrow less money for shorter construction times, and it'll be the cheapest power on planet Earth like it already was. Number 2, regulate for overall public safety, not radiation. Excessive radiation protection adds tremendous direct and operational costs to every aspect of a power plant. It comes to about $10 billion over the lifetime of a nuclear reactor. And every year, we continue to increase control over radiation, even though it's already regulated at levels 10,000 times lower than anyone has ever been hurt by it. And number 3, engage the fossil industry to kick off a development spree. They know better than anyone how to construct large buildings with pipes in them. They have access to the capital, political, and customer relationships. And once built, all they need to do is start pumping fuels from the air instead of from the ground. If the world builds the equivalent of 40,000 1960s light water reactors, we can capture 1,000 gigatons of CO2 and create roughly $500 trillion of products and fuels along the way. This may seem like a high number, but it's not. The energy industry is already a $6 trillion a year business, and so over 20 years, it would just be the equivalent of quadrupling their market size, which we should be eager to do, especially if we want to bring 3 billion people out of poverty. Well, I've given you my insights, so as I conclude, just remember, you here in this classroom are going to become masters of the magic within the atom. You will hold the keys to saving the world from climate change. Just don't let fear hold you back. Thank you. I would be happy to take questions. I know that was a bit provocative along a couple lines. So let's see what you guys have to say.
Please. It seems behind all of this there is an enormous monster called economy. There are a lot of interests in that things don't change, from what it is right now. Do you think it's possible to reconduct the industry to make this possible at the same time to make it attractive to the industry, like generating money to avoid the impacts of the changes?
Listen, your thought is exactly what I was thinking. And as I was trying to derive a path forward out of this first principles approach, that constraint that you just set was one of my #1 concerns. And so that's why I think this needs to be done in a way that doesn't ask people to change behavior. It doesn't ask people to change, overhaul all their factories overnight. It has to be done with the minimum impact on the way that things are working today. So I think the easiest transition would just be whenever they're going to build a new oil well somewhere, instead put together a nuclear reactor and start pumping fuels from the air at that location instead of from the ground. You do that enough, things start to change, the economics start to change. Over time, the world starts to change. Maybe at some point we can get to hydrogen economy for fuels, but your concern was my concern as well. And so this is what I think is the easiest societal transition.
Can you please go over a little bit more in detail about the technology that you mentioned, that you use like electricity generated from a nuclear power plant to get carbon from the air to then get gasoline?
Yes.
Can you go over a little bit further?
Of course. Electricity or heat. We've known how to do this since the early 1900s. We've had the processes to do this, and they've done this on nuclear aircraft carriers previously as well when they want to make jet fuel, essentially, on the ocean. Essentially, there's nothing complicated about separating CO2 from the air or from the water. It's also dissolved in the water. And then breaking off the carbon, and then doing the same with water and breaking off your hydrogen, and then building back up a hydrocarbon from your constituent elements. The only problem is it is extremely energy intensive. So that's why the constraint is that you need to be able to produce heat 3 times cheaper than just burning the fossil fuel to begin with in order to create that same fossil fuel cost competitive way. Now, once you have your constituent elements separated, your hydrogens and your carbons, some of that would be made towards fuel, which would immediately neutralize the carbon impact of fuel, because if all your fuel comes from the air to begin with, you're in a carbon neutral manner. And then some of it would go towards making products, plastics, and that would sequester the carbon for thousands of years. So a combination of fuels and plastics.
But this is just like chemical synthesis. It's not definitely my area. So gas methane would probably be the simpler thing to do.
Yes, that would be so methane would be the absolute simplest, and then you can build from there. Exactly.
With energy.
With energy, carbon, and hydrogen. And then a few other things too for plastics.
With the energy from the
From
nuclear
you need,
power
yes.
plant.
In order to enable this, your energy source needs to be so low carbon that you're not just increasing your carbon debt as you go. And that's how I derived that nuclear, and listen, I'm not from the nuclear industry, never studied nuclear engineering, never met a nuclear engineer in my life before I started this process. And this is what the math showed, that only nuclear was low carbon enough, abundant enough, consistent enough to enable this at a global scale.
Yeah, and so this would be kind of like building nuclear power plants not to power people, but to make extremely expensive
Fuel.
Exactly.
Both, yes.
That's the goal. So to speak.
Yes, and then over time you transition from making the fuel to just making hydrogen or electricity as the economy gradually transitions over time.
If that fuel is going to be burned anyway, aren't you kind of like not solving the problem?
On the fuel perspective, it's carbon neutral, but that is so you can immediately access existing supply chains, and so you create the least possible disruption to society, but you can immediately neutralize the impact of burning fossil fuels.
And then so let's say that you try to go negative, which means that you're gonna take a lot, you're gonna make plastics.
Correct.
Okay, so then we may end up having a different environmental crisis, which is like lots of plastic trash.
I
We
think-
already have it.
I think you're confused, and I understand why you're confused. The media has conflated plastics with being a bad thing.
Yeah.
What it is plastics in the ocean are a bad thing. Plastics, parts of plastics maybe getting to your drinking water or something is a bad thing. That is not plastics. And in America, our plastics do not go into the ocean. It's only in countries with sanitary issues that contribute to the plastic problem in the ocean. Plastics are not bad. People will convince you of that. The media will report on that. They will create that idea, but plastics are amazing. Who else has got a question? Please.
What would be the incentive for big oil and big energy to create a nuclear power plant instead of creating a company or a factory that they know how to create, that they already have the plans for, and they just have to follow a design versus taking the jump into something new?
I'm going to pull two things out of that question. The first is to challenge your assumption that they don't like to build new things. The fossil industry are pioneers in terms of building new technology. They build bigger and bigger things, badder and badder, better than everyone, and their facilities, which are $10 billion facilities, like they do actually a really good job with first of a kind $10 billion facilities. They're always experimenting in new things. When they build a new oil platform that's $10 billion out to sea, it's essentially a completely new first of a kind project to try to capture fossil fuels cheaply. What I'm suggesting is that they take that exact same attitude, and by powering direct air capture with a nuclear power plant, they can also find and produce the same type of fuels they've always done, but cheaper and in a carbon neutral or carbon negative manner. So the key is you have to convince them that it really can be done cheaper than they're extracting fossil fuels today.
I guess my only statement would be that nuclear energy has been around for a long time, so if they were going to make the jump into a new and exciting fuel industry, why would they have done it already?
They've tried. Exxon tried to get into the nuclear game in the 80s, and I think a few others too. Total and a few other companies have tried. Every single time, and I speak to these engineers, and they're like, I cannot believe how obsessed with regulation and safety these nuclear engineers are. They're killing themselves. I don't want to have anything to do with this industry. So I think it's the cultural issues within the nuclear community that we need to tackle first, and then invite in these other players who have experienced engineers and have tons of capital. Please.
You make an equivalence between energy and quality of life, and the majority of the world, the developing world, hasn't really achieved that quality of life because of the lack of energy. And so your idea is that they translate to all those areas where these engineering solutions, they don't even have engineers. I mean, there are some other factors, workforce development, if they're going to follow a plan to do carbon neutral or negative, but they don't have the technology to even understand the problem, let alone, I mean, as the rest of the world kind of catches up to our energy consumption, do you envision roadblocks for enacting these kind of approaches outside of sort of our first world resources?
Yeah. I mean, I think it's going to have to be the first world companies and countries that start deploying this infrastructure abroad first. But I would give these developing countries a ton of credit. I mean, they are stock full of brilliant people whose potential is just being totally limited by access to prosperity, to education, to energy, right? And the minute that we give them energy, we'll go over there and we start building these plants for them, and we make it so they don't have to spend, half their day doing the things that modern electricity does for people. I think very quickly you'll see burgeoning growth in all sorts of sectors in their economy and way of life, and they'll be able to take over in a sustained manner from there. I also don't think necessarily that these plants have to be everywhere. With this idea of pulling carbon from the air and then distributing carbon negative fuels and products around the world, the whole thing could be done on Greenland, and it could become the synthetic Saudi Arabia of the world. So I think there are a few ways that the developing world could engage with this type of technology.
Please. I had a lot of questions. Thank you for your presentation. One of the things that you sort of had based a lot of this off of is if we went carbon neutral, then the amount of carbon in the atmosphere wouldn't change, and we would continue driving at 30 miles per hour to continue that. There are lots of natural systems that remove carbon from the environment, for example, the trees and the other plants in the plankton. If we went carbon neutral, what is the predictive effect of those forces on minimizing carbon content in the atmosphere? And how does that affect?
Yeah, that's a good question. No, I like the way you think. I started off with that same, okay, so before I found nuclear, one of the calculations that I ran were, what if we were just to genetically engineer trees to grow faster, taller, better, and plant them all around the world, right? That's where I started, trust me. But the bounding conditions that I always subject myself to is, does this scale? If you were to have all perfect conditions across the board, does this scale to the level of the problem? And what I found was, even given the best circumstances, we maxed out at sequestering 200 gigatons of carbon over the next 20 years. And that's if you plant every square inch available with trees, super trees. And then the problem there is that it would take 20 years to grow. They don't capture carbon anymore after that 20 years. And we've already created 200 gigatons worth of more problem in just the next 5 years. So listen, I love trees. I think we should do it anyway. Great ecosystem benefits. I have plants in my home. I love clean air and the feeling that they give. But they are not the solution to our climate problem.
Absolutely. I'm sorry. I was wondering about the potential of maybe, at the very least, reaching a carbon neutral state and letting the trees slowly let us reverse from there, if that would actually be somewhat feasible, and not by engineering our own.
Yeah, I get it.
Simply letting the globe do its thing.
Yeah, so the problem is, let's say we reached a carbon neutral state and then let the trees take over. It would be far, far too slow, and the heat would just continue to climb, and then we'd be at that next tipping point before they could do what they needed to do. And when you think about it, that makes sense, right? What we're burning right now, what we've burned over the last couple hundred years, is about 100 million years worth of tree growth that was shoved underground, okay? So we've already burned 100 million years worth of tree growth. So we can't expect another 20 years of trees to do much for us.
I understand that. Please.
I'm a retired nuclear engineer from the nuclear industry. You avoid mentioning what I consider the elephant in the room here.
Yeah.
How do you convince the Nuclear Regulatory Commission to accept more common sense engineering?
Yeah, it's interesting. I've spent a lot of time with the NRC and also spent a lot of time with foreign regulators as well. I've actually seen from the NRC leadership an interest in what they call a transformation, a change in the way of doing things. However, it is very, very difficult to have institutional transformation in any type of organization, even in a normal corporate environment, without firing a ton of people. And the NRC isn't going to do that. Most government agencies wouldn't. That's one of the benefits of working for a government agency. You get to keep your job for 30, 40 years. So I think the NRC is going to have a really hard time righting the ship. But there are 180 countries with the sovereign right to develop nuclear power, and there's about 40 other well-established nuclear regulators out there of all different shapes and sizes. Some of them are probably small and agile enough to institute total reformation over the way that they think about allowing nuclear companies to develop their products. And so that's part of the work that we do at the Energy Impact Centers. We go around the world meeting with various stakeholders across industry, government, regulators, and trying to figure out who's on board to actually enact this type of vision.
Please.
Do you find more pushback from like NRC and regulatory commissions across the world, or do you find more pushback from utilities and manufacturers of power plants?
Both.
Anyone in the nuclear industry is kind of really sucked into the safety culture, which I think is pretty heinous because, like I said, it's not public safety. It's radiation safety is all they care about. If they cared about public safety, what they would do is they would run that same coal calculation and say, we're replacing a worse energy source. Even if our plants blow up and kill a few people here and there, so long as the net effect is we've reduced coal deaths, it would totally be worth it. And I haven't met a single person in the entire nuclear industry who feels that way. Even though it's not uncommon in other industries, transportation, in medicine, you are allowed to bring to the regulator and say, listen, penicillin, we know it kills people, but you know what? It's better than non-consumption of antibiotics. It's better than these other antibiotics. We're going to take a few deaths for the greater public good, and the regulator stamps off on it, so long as you can prove it's better than the alternative. And no one in the nuclear industry feels that way. It's been 50 years of promoting this safety culture.
So you've mentioned the fact that airtight vessels are one of the issues. Well, if you don't have an airtight vessel, you can't really have a pressurized water reactor.
That's not true. I meant to distinguish that the containment dome, the containment structure outside of the pressurized water reactor doesn't need to be airtight.
Okay.
And in the case of a meltdown, it's a mess in your room. It's just a mess, and that's it. And yeah, maybe you shut down that facility, maybe you remediate it somehow, but it's not a public safety hazard.
And was all this done with this calculation of large-scale nuclear power plants, or was it considering the effects that Gen 4 reactors could have on the industry?
Yeah, let's talk about the next generation of reactors. I've gotten now to meet, I had the privilege of meeting almost 50 nuclear startups at this point, all of which I think are true heroes of the environment. And it's hard, guys. It's hard being a nuclear engineer, right? Like people don't understand the technology, and it's got kind of a bad rep. And so these guys to go out and then promote a new technology, I just think is just so awesome. The one thing that I would caution them is to not say that they've got a safer reactor than before. When they say they have a safer reactor, what they're doing is they're scaring everybody into thinking that there's a huge inherent danger to the technology, even theirs. And so they're shooting themselves in the foot when they say that their technology is safer. For any advanced technology, the only thing they should be selling is cheaper. Cheaper, faster to deploy, fits better within your grid. It should be the economic benefits that they're championing and not the safety ones. They should shut up about safety. Now, that being said, even though these are some amazing reactors, I think that they will be the future of this technology 10, 20 years from now. You've got a steep learning curve of material handling, construction, manufacturing processes when you deviate from the standard supply chain. So I think the next 10 or 20 years of explosive growth within the nuclear sector should be with things that utilize the existing supply chain, which is probably a pressurized water reactor or boiling water reactor. There's some modifications you can make, but newer chemistries, newer materials, newer welding processes, newer ASME certifications, all these things take a long, long time to bring to fruition. Even if they're better, it's hard to get to scale faster.
I think we're towards the end of our time. So 1:50, so we all thank our speaker one more time.
Thank you. Thank you guys for listening. Really appreciate it.